Okay, so before the break, we have our very first researcher team. And we have Lisa Wingen from my group and David Herman from the Kleinman group and the Air Pollution Health Effects Lab. So I think this is a really good example of the collaborations that AirUCI encourages and engenders that you really can't do unless you talk to each other. So I'm going to turn that over to them. And so let's see, are you going to use the podium or
I'll use the microphone.
the mic? Okay. Okay, and you're going to use the podium. Okay, and then there's a pointer on that.
Okay. Let's make sure that works.
Thank you.
You got it. Hey. I can explain to the ones who didn't get it. Okay, is this close enough? Good morning, and I'm very excited to be here and to be presenting collaborative research between the Kleinman group at the Air Pollution Health Effects Laboratory and the Finlayson-Pitts group in chemistry. Particles in the atmosphere are small enough to be inhaled into the deep lung, but the damage from particle inhalation doesn't end at the lungs. The smallest particles are able to move into the bloodstream where they can have major impacts on cardiovascular health and heart function. We hope to convince you of that today. One approach to studying the health effects of particle inhalation is to draw in local ambient air pollution and use that for health effects studies on animals. A nice advantage of that is that the particles represented are those from the real atmosphere that we breathe in every day. To set up a study like this, we often use a particle concentrator, which will increase the concentrations in order to have a biological impact on the animals over the time period of the study. And the concentrations are increased by about a factor of 10 over ambient. But note that these concentrations are still at least a factor of 5 smaller than concentrations found in places like Beijing, Mexico City, and other urban centers around the world. So once the particles are concentrated, they're delivered to mice who are prone to developing plaques in their arteries. And the mice inhale these particles on and off for about 2 months, and that's equal to about 20 years for a human. During and after the exposures, a variety of health-related observations are made in the animals and compared to animals who are inhaling particle-free clean air over the same time period in the same manner. One of the questions we have, though, are what types of particles or what components in the particles are the most toxic? And to help us answer that question, we intentionally change the particle composition. We do this, in this case, using a thermal denuder, which is essentially a heater, and it will strip off the most volatile components in the particles. We then have a third group of mice that's inhaling these different particles. But how do we know those particles are different? Well, we have a variety of particle measuring equipment to get characteristics about the particles, including diameter, composition, mass, and number concentration. And we have a demonstration later. One of the instruments is an aerosol mass spectrometer, which you can see a demonstration of later today through a live video feed into the laboratory. So are the particles really different? What do they look like in the first place? Particles in Irvine look a lot like typical urban particles. They have a large organic component shown there in green, some inorganic components as well. And when we concentrate those particles, we find that they are very much the same. Yay, nice check. We want the particles that are concentrated to look the same as ambient particles, because those are the ones we're breathing in every day. However, when we use the thermal denuder on these particles, we find that they're very different. We strip off the most volatile components of the particles, and what that translates into is almost all of the organic component is removed from the particles. Some of the inorganics are removed as well, the more volatile inorganics. But those organics that are left behind are the more oxidized particles, so behaving a little more like aged particles. And now our question is, which particle, now that we have these two different particles, which particles are more toxic to inhale? And that's a question only David can answer.
So after we collect and expose our mice, we collect a series of tissues. We collect anything from organs to bowel fluid to blood, and we can measure anything from total organ damage to immunological response to even cholesterol in the blood. But today I'm going to talk to you specifically about how inhaling this particulate matter can mess with atherosclerotic plaque development and how it can alter electrocardiogram responses in the heart. So first, let's talk about atherosclerotic plaque development. And right here we have an image of the ascending and descending aorta. And the plaques we look at form most large in the aortic arch and the A1 or brachiocephalic artery. And if we zoom in at the brachiocephalic artery, we can see two cross-sectional images. The bottom we have an image of the brachiocephalic artery of mice exposed to concentrated PM, and on top a corresponding of a mouse exposed to clean air. And what we can see is that when we expose these mice to this concentrated particulate matter with the semivolatiles, you get this enhanced atherosclerotic plaque accumulation, and that's composed to the clean air mice. These are just representative, but we have nice data and graphs to back these up. And we see that when you strip off the semivolatile particulate matter, we see that the results are somewhere in between these two. So we see that the semivolatile fraction by removing it, we can kind of attenuate these plaque progressions in these mice. But we found that particulate matter inhalation doesn't just hinder these plaque progressions, it also has alterations to normal cardiac sinus rhythm. And so we implant these mice with telemetry devices and monitor them continuously through the exposure. And we can use these ECG images to detect changes in heart rate, and we can also look at specific parts of them to look at alterations in cardiomyocytes. And when we first look at the heart rate changes, we can see that when you expose mice to this whole particulate matter with the semivolatile fraction, you get an increase in PR, or in atrial relaxation phase, which is the PR interval, and a slowing down during the ventricular relaxation phase. But when you remove these semivolatiles, we get this attenuation effect, just like with the plaque progression. So that's pretty straightforward. It seems by removing this semivolatile phase, you can kind of dampen these responses. But we also wanted to figure out, how do these particulate matter particles affect cardiomyocytes and influence things like cardiac ischemia? So when we look at those endpoints, it's not so cut and dry, because when we expose mice to either stripped or whole particles with and without the semivolatile fraction, we get large responses. So within the T-wave area, amplitude, and elevation, those are all ways we can identify cardiomyocyte damage, which are indicative of cardiac ischemia. And it seems to be the case that when you expose these mice to either the stripped or whole particulate matter, you get large alterations in these ECG waveforms. And what's important is that even with this semivolatile-free particulate matter, it can elicit changes that are as big and even in the opposite direction of whole PM. So it seems to be the case that the constituents within this particulate matter are important for us to identify, because those constituents seem to be involved in the ultimate health effect. But particulate matter, as we've been talking about, isn't the only component of air pollution. We're also looking at ozone a little bit, and we've found that when you expose mice to particulate matter, when there's been a high ambient ozone level, you see increase in these electrocardiograph waveform anomalies. So we've done some co-exposure work a little bit already, and we found that when you do these co-exposure atmospheres, we've gotten results that aren't additive or synergistic of these single exposure atmospheres alone, and the results are even counterintuitive, meaning we get this blunting effect back down to the air levels when you have this co-exposure mixture. So it seems to be the case that ozone and particulate matter exposures aren't additive or even generalizable, because the particles are always coming from different point sources, so they have different inherent constituents. So with that, I hope we've convinced you that inhaling this particulate matter has, in addition to the lung effects that has been going on for many years, they have cardiac effects and cardiovascular effects. And the answer to solving this large problem may be in something very, very small. And with that, we'd like to close with this picture that Barbara also showed of Jim Pitts. He's talking to then President Reagan about none other than the pressing impacts of lung health risks of particle matter. And with that, we'd like to thank you.